Okay, today we're starting chapter 9, so we're going to talk about vectors. So a vector is a quantity that has both magnitude and direction. If you watch Despicable Me, you've got Vector Man, right? You can think about him. He talks about that. So in general, though, we're talking about it has some, let's say, point A. It's going to have some initial or starting point. And since it has direction, it will have an arrow that goes to some, what they call the terminal or ending point. Okay. They sometimes will just bold it and hey, they'll do a bold V. I also if you're handwriting it, you can do a little V with that little kind of arrow thing on top to represent vector B, or even we can put AB to represent that same vector. Okay. So what does the magnitude of a vector represent? It represents the length of the vector. In general, they'll use kind of this double lines around that to represent the magnitude. In general, since we're finding the magnitude, it's going to be the length, right? And you can kind of think about the distance formula or just the Pythagorean theorem, the square. And since we're doing to solve for this individual value, it'd be the square root of a squared plus b squared. So then lastly, what does the direction of a vector represent? And it represents the components on the vector. So if we have this vector v, they usually write it, and that kind of almost looks like inequality signs, but they're not, that will have an a value and a b value. The a value will represent if we're going to the right, positive, right, or to the left, negative. And the b value, just like you'd expect, represents if you're going up or if we're going down. How many spaces? So that's kind of where it leads to, hey, the magnitude is the square root of a squared plus b squared. Okay, and then another way we're going to think about it is the angle between the axes. And in general, it's going to be the positive x-axis we're talking about and the vector. Okay. So here's a little example. Let's look at the vector 2, 3. So really that means you're going right 2, and we're going down 3, right? So in general, they'll start it at the origin. You don't really, it's kind of arbitrary. You could just have a graph that didn't have a grid on it, but I think it's easiest to put it on an x and y axes. So if I start at the origin, I'm going right 2 and down 3, and that's where I'm ending. But it's more than just connecting those points. Remember, it has a direction, so we have to show, hey, there's an arrow. It's going kind of southeast. If we're talking about magnitude here, though, the magnitude of this vector is going to equal the square root of 2 squared plus negative 3 squared. Which makes sense because you're finding the hypotenuse of that triangle, right? So we got the square root of 4 plus 9. So we've got the square root of 13. Okay, let's look at the next one. This one's representing slightly differently. It's saying we're going from point P to point Q, and they say, first of all, find the vector. So if they just give you the initial and terminal points, we're basically saying, okay, well, how did I get from 7 to 6? Well, to get from 7 to 6, you had to subtract 6, right? 7 minus 1 is 6, but it is going down, left, it's going negative 6. How do you get from negative 1 to 3? We are adding 3. So here the vector, negative 6, 3 is being represented. And if I ask for the magnitude of that is taking the x component, which is negative 6, squared, plus the y component, which is 3 squared. So we get the square root of 36 plus 9, and we get the square root of 45. Which if you did want to simplify that, 45 breaks down to 9 and 5, which then breaks down to 3 and 3. This is equivalent to 3 square roots of 5. Okay, so now let's talk about some operations. In general, these vectors in this lesson, we're going to add, subtract, and then we are also going to multiply by a scalar. So let's just take a look at what it looks like. Find the following with graphing given that A is 2, negative 3, and vector B is negative 7, 4. So if we want to find the sum of a plus b, we're going to draw vector a. So we start at the origin. We're going right 2, down 3. Okay, so this is vector a. And in this case, I usually graph what I call the tip to tail method. Let me see. So what that means, I'll put it over here. So tip to tail. And so what that means is that the terminal point of first vector is the initial point of the second. And I guess I should say then connect original, I'll just say it in words. Then connect the original initial point to the final terminal point. So, okay, we got vector A, and then we're saying, okay, from this point, the same point, so we're going to use now this as our initial point. We're going to go left 7, because that's negative 7, right? So left 7 would put us at negative 5, and we're going to go up 4. So left 1, 2, 3, 4, 5, 6, 7, right? Up 1, 2, 3, 4. So we're going to be at this point. Sorry, right here. So then vector B looks like this. Okay. The actual resulting vector, right, what A plus B, that vector looks like, is this vector right, oh, sorry, I thought I was doing blue. Let's try that again. It's going to be this vector right here, right, connecting that initial point that we started with to the terminal point of the second one. This is going to be vector A plus B. And just so you kind of see it, notice that vector would actually represent, we're going left 5 spaces, so negative 5, comma 1. We're going to talk about the algebraic representation in a moment, so that will kind of help. Okay, the only thing that you do differently when we have subtraction is you can think about it as adding the opposite, right? Right, as the same as subtraction is the same as, right, subtraction. So here what we're really thinking about, when I think about vector A minus vector B, it's the same as doing vector A plus a negative vector B. So we want to find negative vector B. So in this case, let's start with vector A. We know what that looks like. We're going to start at the origin, and we're going to go right 2, down 3. Okay, so we've got our vector A. So now let's talk about vector B. The opposite of vector B, so if I think about a negative of vector B, if it really was negative 7, we're going to switch to be a positive 7, and if it was up 4, we are now going down 4. So we get positive 7, negative 4. So tip to tail, so we're going to start here. We're going to go positive 7, which will bring us to 9, and down 4 more, which will be at negative 7. So we're going to be down here. This is vector B. Okay, so then A minus B, that resulting vector, will be connecting these two. So we get A minus B, vector A, minus vector B. If we count those or kind of look at what the boxes are, we get a positive 9, meaning we're going right now, 9, and we're going down 7, so a negative 7. All right, so let's talk about, while they do want you to understand kind of graphically where this is coming from, and you can now see like, hey, we're just counting the spaces, it's a lot easier to do things algebraically. So if we look at example 4, I have the same exact vectors. So A and B, and they're still going right 2, down 3. And they're going left 7, up 4. If we want to talk about it algebraically, the way that we do it algebraically is we simply add the x components and add the y components. Sorry, I didn't spell components right there. Components. So in this case, when we're trying to find a plus vector b, we're going to take 2 plus from vector b, we have a -7. We're going to do comma, -3 from vector a plus 4 from vector b. So 2 plus -7 is -5. -3 plus 4 is 1. And notice how that matches what we got up there on the graph. So let's talk about vector a minus vector b. We're going to take the x component of vector a, which is 2, minus a -7. We're going to do comma, -3 minus 4. 2 minus the -7 is really like adding, so we get a +9. -3 minus 4 is a -7. And you'll notice these match what we got up on our graphs above. Okay, so now let's talk about scalar multiples. A scalar multiple is draw and find the scalar components of each of the scalar multiples to multiply the vector c by a scalar, multiply each individual component by c. So what we're saying here is if we're trying to do 2 times -4, comma -3, that's the same as doing 2 times -4 and 2 times -3. So we end up with a vector of -8, -6. And notice there it's still going the same direction, just double the distance, right? Twice as long. 2 times longer. Okay, this one we're going to do -1/2 times the vector. So in this case, we would have -1/2 times -4, right? And we'd also have -1/2 times -3. So this time we'd get a +2 and a +3/2. This one did two things. Notice how it switched directions. So rather than going left and down, it now goes up and to the right and to the up, and it's half as long. Or I should say half the components, right? Half the x and y components, or twice the x and y components. Okay. Because technically there, be careful, the length is like a squared plus b squared. So here, while we did that, the actual magnitude of these may not be quite maintained there, right? So I just think it's good for you to see like a little visual. So if we wanted to think about these different ones, our vector v originally, if we start at the origin, I go -4, left 3. It is this vector right here, right? This would be vector v. Okay. If I now go in and draw in vector 2v, I'm now going to go to -8, -6, right? So see how it still goes through there, but it's twice the distance now. That one actually really is twice. Okay, so it is twice. And now, if we go right 2 up, 3/2, I have the same slope. I totally graphed this wrong. Sorry, okay, let's go back for a second. Sorry, I apologize. On these ones, sorry, I went down 4, right 3, but I should have gone left 4, down 3. Okay, so now this is vector v. Okay, we're looking a little better. And now we're going to go left 8, down 6. This is vector 2v. Okay, it is twice the distance. Okay, so now if I start here and I go right 2 up 3/2, this is your -1/2 v. So notice it is in the opposite direction, but it still has the same slope, and it is, in this case, half as long. Okay, so now let's talk about in general. And for the record, it is really twice as long and half as long. The magnitudes work out the same. Yay! Okay, so now let's talk about what this really means. So when you multiply a scalar, it changes the direction and or the size of the vector. Right, maybe I should say that the length of the vector, like the magnitude. That'd be the fancy way since we're in college here. But it does not change the slope, okay? So multiplying by a negative causes the direction to be switched. In general, though, if you multiply by 1, right, that's not going to change. Okay, so now let's go ahead and see what this does. So if we're going to use these two vectors, u is 12, negative 5, and vector v is 3, 4, if we just ask you to add them, the easiest way is to do your algebraic, so add the x components, add the y components, and we'd end up with 15, negative 1. Okay, in this case, when you've got vector u minus twice vector v, I would probably go through and think about order of operations. Do I multiply or subtract first? We are going to multiply 2 times vector v. So then we would get vector u minus 6, 8, right? We multiply both those 3 and 4 by 2. So what do we get there? We're going to do 12 minus 6, right, our x's, and then our negative 5 minus 8, and we end up with 6, negative 13. Okay, this one's a little bit different. Notice how this one's saying, okay, you're taking the magnitude. So like these two, they call, these two are both vectors, right? This is a vector. This is a vector. But when they ask for the magnitude, you're going to get a single length, right? So these are actually called scalars, but they're saying, well, take a vector, they're saying, what is the magnitude, right, of the vector when you add u plus v? So of the vector 15, negative 1. What's the magnitude of that? Well, to do that, we're going to do the square root of 15 squared plus negative 1 squared. So 15 squared is 225 plus 1 means we get the square root of 226. If you wanted to think about kind of seeing what that divides down to, 226 divides to 2 and 13. So, 2 and 113. So that is prime, so therefore you can just leave it like that, or they may ask you for a decimal approximation. So this is what they call a scalar technically, right? It's just a single unit. Okay. And then this last one is a little bit different because notice here the operation. It technically wants you to find the magnitude of u and then add it to the magnitude of v. So I'm actually going to do a little side work over here. The magnitude of u is going to be the square root of 12 squared plus 5 squared. So the square root of 12 squared plus 5 squared is 169. And the square root of that is just simply 13. Whereas for vector v, the square root of 3 squared plus 4 squared is the square root of 25, so we get 5. So we get the value of 13 plus 5, and we get 18. So notice those are, while they both are scalars, right, they're an individual number, they're a length, they're not the same because what's happening here is we're finding the hypotenuse of our two vectors, and then we're adding those two hypotenuses together, right? Whereas in the one before that, we combined it to make one big triangle and then just found the hypotenuse of that. So just be a little careful about operations. Okay, the quantities described known as magnitudes are known as scalars, right? Whereas quantities that are described both by magnitude and direction are called vectors. So from a vector, you can always find the magnitude, right? But it's got to have direction as well. Okay, so now let's look at kind of relating it more back. That gives you your intro. Let's relate it more back to what we have been doing with trig. So it says, find the component form of vector v using the information about its magnitude and direction. So here they're telling you got this vector has a magnitude of 6, so that means it has a length of 6. It lies in the standard position, it lies in quadrant 1 with a 60-degree angle on the positive x-axis. So we're talking about this triangle, right? The magnitude is the hypotenuse, which is length 6. And they're basically wanting to find the x and y components, right? So I'm going to do like kind of the math behind it, and then I'll kind of show you a shortcut. So here, if I wanted to find x, let's say, that's the adjacent, and I have the hypotenuse, so we're saying cosine of 60 degrees equals x over 6. Multiply both sides by 6, so you get x equals 6 times cosine of 60. But we know that cosine of 60, right, that's one you should recognize. 30, 60, 45 should be ones you know off the top of your head. We know that's a half, so 6 times a half is equal to 3. We could do the same thing with y. Y is the opposite, and we have the hypotenuse of 6. So we're going to do sine of 30 degrees, sine of 60 degrees equals y over 6 times both sides by 6. So y equals 6 times 60 degrees. Sine of 60 is square root of 3 over 2. So then we get 3 square roots of 3. And you may recognize that from your 30, 60, 90-degree triangle anyway. Like if you knew that, you would know that the side across from 30 is half the hypotenuse. That may be another way to do it. So here, your x component is 3, your y component is 3 square roots of 3. So this is the vector that they're talking about when they say vector v. Okay, so the kind of shortcut here, if you wanted to think about it, which makes sense, this all relates to our trigonometry, is we're taking the length of the magnitude, right, of our vector, which is the hypotenuse, and we're going to multiply it by cosine for our x value of the theta, and then sine for the y value of our theta. And that will be your, always be your vector. So, if you remember, that kind of makes sense, right? Cosine always goes to the x, sine goes to the y. In this case, we're just taking it times that component. Vector, magnitude vector. Okay. I do think the picture helps, so I'm just going to draw at least one, maybe two more pictures. Well, at least one more picture, and then maybe we can use the shortcut on the last one fully. So on this one, we're saying, okay, here, we're in the second quadrant, and it makes a 30-degree angle with the y-axis, so 30 degrees there. And then they're saying, hey, this hypotenuse is 2 square roots of 3. So in reality, think about this angle from the positive x-axis is a total of 120 degrees, right? So while we're finding this x and y, the theta we're going to use is 120. So whether you want to kind of set up your proportions, or we're just saying, okay, well, my shortcut says I'm going to take 2 square roots of 3 times cosine of 120. And that's the part you got to be careful about, that you didn't just plug in 30. Sine of 120. So here we'll have 2 square roots of 3. And then we do cosine of 120 is negative a half. And then sine of 120 is the square root of 3 over 2. Okay, so when I actually multiply 2 square roots of 3 times negative a half, I get negative square root of 3. 2 square roots of root 3 times square root of 3 over 2. The 2's will cancel. Square root of 3 times square root of 3 is 3. So we have our resulting vector. Okay, last but not least, if we want to just kind of go straight to the shortcut here, although you could draw it, it looks kind of like a similar picture to up above, where it's in the second quadrant, the angle is 117, but then the hypotenuse is a lot longer, it's 392 this time. We're going to take that magnitude of 392, and then we're doing cosine of 117, sine of 117. This case, since we're going to approximate, I'm going to write it as 392 times cosine of 117 and 392 times sine of 117. At this stage, it's simply plugging in your calculator, right? 392 cosine 117, and you get, let's do 2 decimals, you get approximately negative 177.96. Do the same with 392 sine of 117, and you get 349.27. Okay, last but not least, let's look at this word problem, right? So we got a small boat that leaves camp whatever and heads across the river at 17 miles per hour. That is with respect to the water at a bearing of south 48 degrees. The river is flowing due east at 8 miles per hour. What is the boat's true speed and heading? So let's first think about this picture. I always think a picture helps. So they're talking about going south, and then they're going 68 degrees west. So their actual heading is this way at 17 miles per hour. Okay, the problem is, since we got this river and it's flowing due east, so due east is going to go directly that way, and then this is at 8 miles per hour. So if you think about where you're actually headed, if you were in this boat, you were going to head along this red line from the initial point to the terminal of that, right? Think about adding those two vectors, right? You're going to be, right, you're not going to go the exact direction you were initially headed because of that stream. So let's talk about the first thing it asks for, and maybe I will redraw this triangle because I always think that helps me kind of see things. I've got 17 miles per hour here, and then this is 8, and they want us to know, first of all, like the actual true speed of the boat is going to be this x, I'll call it, the last side of our triangle. So let's see if we know any of these angles. It may kind of help you to always set up your parallel line. So if this is 68, so is this. And this time we also have a 90-degree angle. So 90 minus 68 degrees leaves us with 22. So this right here is 22 degrees. In this case, since we have the two sides and the angle between it, we're going to use the law of cosine. So x squared equals 17 squared plus 8 squared minus 2 times 17 times 8 times cosine of 22. So we get x squared equals, when you type all that in your calculator, you get 100.808, and then we're taking the square root. So I got the nearest mile per hour. So I got the square root of that, so I got like 10.04, so we're going to call that 10 miles per hour. Okay, on the next part though, so that is the speed, true speed, boat's true speed. The next thing is they're really asking you for the bearing. So they're basically wanting to know, if I look in this picture over here on the right, they're wanting to know what is this angle right here, because that will give us a nice direction from south. So if I find out the alpha at the top of the triangle, then I will be able to kind of subtract things from 68 to find out the actual bearing. In this case, since I'm looking just for this angle, I always think, even though this is 10, I think the law of sines is a lot easier to use. So I'm going to do sine of alpha over 8, and then I also have the 22, so I'm going to do sine of 22 over 10. Do your cross multiplying magic. Do a little division there, right? So 8 times sine of 22 divided by 10, and you get sine of alpha is 0.2997. Take the inverse sine of that, right? And you end up with equals alpha, so we end up with alpha equals 17.4 degrees. So, although this is 17.4, that's really for where the boat is headed, right? If we look over on the left, we got the whole 68, and we got to subtract where that actual angle of 17.4 is, so 68 minus 17.4 gives us 50.6. So the angle we were looking for right here, this is 50.6 degrees. So they're headed south 50.6 degrees to the west. And this would be the boat's bearing.